All right, hello, welcome to Torque 101. Remember, this is Torque 101, so if it's too basic, you can tune in for Torque 202 as we prepare that in the coming months. In any case, let's get started. Today, I thought we would just touch on a number of things that come up frequently when we're talking with customers. Basically, as we talk to customers, I'm spending a lot of time on the phone talking with customers, and a lot of our reps are out in the field visiting customers. Our regional sales guys and myself go out and visit customers. We end up with a number of kind of common questions that come up over and over. So some of those will be addressed in this presentation. We'll talk about some definitions that relate to torque, talk about what is a torque transducer, talk about different types of rotary or different types of torque transducers, rotary reaction, shaft versus flange style, talk about mounting, we use couplings, talk about fixed or floating mount. Sometimes we need to use bearings. Sensors have bearings. Sometimes there also need to be bearings in installation. We'll talk about that a bit. Accuracy and resolution. You know, when you're selecting a sensor, how do you decipher the data sheet to understand what accuracy you're going to get, or how do you understand what you might need? How to choose the right capacity. Talk about dual range sensors a little bit. Talk about RPM considerations, some common features or commonly desired features of torque sensors, and also we'll go through a few torque applications. Next up, very quickly, torque equals force times distance. For force, we measure that with force sensors called load cells. For torque, it's a torque sensor, essentially the same technology, but with torque, you're measuring a force applied at a distance from a center of rotation. Typically, it's going to tend to make something want to twist, and we measure it using a torque transducer. Couplings are used to mount torque transducers into a drive line. Typically, they have to be flexible. Sometimes rigid couplings are used. Backlash is a feature that's typically undesirable in a drive line, and that would have to do with if there's some movement, say within the coupling in a shaft, whereas you reverse direction, you may get some slop in the connection. Bearings are used to support rotating elements and also to take extraneous loads. Accuracy is a little difficult. People want just one accuracy number in many cases, but it comes down to a number of different factors that affect the accuracy. We'll talk about some of those. Resolution, again, that kind of plays in with accuracy. What are you trying to measure, and how well are you trying to resolve, or how precisely are you trying to resolve that measurement? Noise comes into play as well. If you have a lot of noise in the system, it's hard to get a lot of resolution. Signal-to-noise ratio talks about if you're trying to use a sensor down, you know, at very low range or low portion of its range, you may have a lot of noise relative to the signal, and that would be undesirable. RPM considerations. RPM is rotations per minute, and it's the speed of rotation, and that's the unit that's commonly used in the US and in Europe. So, what is a torque transducer? Many of us are familiar with load cells. Interface makes strain gauge based load cells and use foil strain gauges for those sensors. A torque sensor is very much the same, except it reacts to torque instead of force. But there's basically a metal spring element that is called a flexure, and that deforms under load. Strain gauges are bonded to the flexure in a Wheatstone bridge configuration, and then when torque is applied to the sensor, it causes either a bending or a shear strain in the gauge area, and that causes the strain gauges to change resistance, and that generates an output voltage signal proportional to torque. And so this is the basis of torque measurement using foil strain gauges, where a flexure element deflects, and that is converted into an electrical signal that can be correlated to applied torque. You can see in my picture, this is our one of our model MRT torque sensors. Whoops. And you can see the strain gauges would go on the sides of these beams, and that would be in a bending configuration. These are just a couple type of elements that could be used for torsion. A basic element might be a smooth, solid, round shaft A square shaft would be a little more involved. Makes it easier to strain gauge, not necessarily better performance, but it's easier to strain gauge a flat surface. Hollow cruciform is like the picture we showed previously, and that basically machines beams that bend under torsion. We have two different types of torque sensors we talk about commonly, reaction and rotary. That's sometimes confusing to people. Obviously, rotary ones spin, reaction ones don't, but what is the real difference between the two? So to start off, we're talking about reaction sensor, and that's a sensor that has a strain gauge sensor, like we said, measures torque. Typically, though, to get the signal off of the strain gauge area and to apply the power to the strain gauge bridge, we have to have a cable attached. And so a reaction sensor has a cable, and that cable or connector is attached to your instrumentation, and if you were to spin that sensor, the cable gets wrapped up and causes problems. So a reaction sensor could rotate. The only thing that prevents it from rotating is the cable. Now, in many cases, in tests where there's only a limited amount of rotation, a reaction sensor can actually be used. If you imagine if you have a valve test where you're twisting the valve back and forth through 60 degrees, for example, you can easily use a reaction sensor for that measurement. The one caveat is you would have to make sure that the cable doesn't wear out as it wiggles back and forth during the test, and so some method of strain relief for the cable needs to be in place. Now, a rotary sensor basically takes a reaction sensor and allows it to spin. So it's exactly the same sensing technology. It's just if it's going to spin, you have to have a way to have the power. You have to bring the power onto the rotating shaft or rotating element, and then you have to have a way to get the signal off of the rotating element. Now, very commonly, slip rings have been used, and that's where each leg of the bridge has a ring on the rotating element, and then there's a corresponding brush that touches that ring and provides a slipping connection from the rotating element to the outside world. Rotary transformers are probably a better technology, I would say, where that gets rid of the slip rings and uses transformers to bring AC signals to the bridge, and then or power to the bridge, and AC signals off the bridge. And then those can be fancier by adding amplifiers and things into the circuitry. Some sensors actually have rotating electronics, and they may digitize and pulse a digital signal off the rotating element. And then radio telemetry would be using actual radio signals to transmit the sensor data off of the rotating element. But all of those are various ways to get around the issue of an attached cable. So at the heart of every rotary sensor is a reaction sensor. This comes up pretty frequently. Customers want to know, okay, I have a rotary sensor, but I'm only going to be spinning it at 2 RPM. Is that okay? And the answer is absolutely. It doesn't matter. It doesn't have to spin at all. A rotary sensor does not have to spin, but it is allowed to spin if you want it to. And of course, some applications, the sensor must spin. For example, if you're measuring the power of a motor and you want to measure it in line on the shaft, the sensor has to spin to make the measurement. But on the other hand, the sensor itself doesn't require that it spin to work. This is an example of a reaction sensor. Now, when we talk to a customer, typically we want to try and key in on the method of measurement that works best for his application, but also is lowest cost and easiest to implement. A reaction sensor, in many cases, can be a better way to go than using a rotary sensor. They're less expensive, they're less complicated, less to go wrong, and so it should be at least considered in most installations to understand if a reaction sensor could be used. This is an example where a hollow reaction sensor is bolted between a plate and a motor, and then the motor shaft passes through the sensor and then spins. And as the motor shaft spins, the housing of the motor wants to spin in the opposite direction. The torque sensor prevents that, hence the term reaction torque sensor. These are quite commonly used in this way. Of course, the sensor has to be hollow. There are some considerations with the weight of the motor can cause problems. To alleviate that, the motor could be supported, say, on bearings or some way to keep it from applying too much load to the sensor in a bending orientation. But this is a pretty good installation. in some cases, the trick is you have to be able to mount your motor to the reaction sensor, and you have to be able to mount the reaction sensor to whatever it is that you need to mount the motor to, basically, and that can require adapter plates or whatnot, and certain motors lend themselves to that more than others. Some more examples of reaction sensors measuring rotary torque. You have a motor that's mounted to a torque sensor rigidly, and then the shaft is actually attached to a brake. You see the left side, we're trying to measure motor torque, so basically maybe we're testing a motor, and so the sensor is actually connected to the motor, and we're using the brake to provide the load. On the right, you have a similar but different setup where we have the motor connected directly to the brake, and then the sensor actually holds the housing of the brake. And so as you apply your load with the brake, the housing of the brake wants to rotate, and the sensor is used to prevent that. Slightly different in that if you're trying to measure motor power, you want the sensor connected to the motor, and you don't have to worry about the losses through the brake due to heat. On the other hand, if you're trying to measure the brake torque, you may want to actually put the sensor on the brake. And then in some cases, you can imagine you might want to measure both, and then you can envision a situation where you have the sensor, or two sensors, one mounted on the brake side and one mounted on the motor side. These are some examples of a rotary sensor. You can see there's a difference where there's a load or a motor and a specimen, and they're outboard, and then you have the sensor mounted inboard. And so the sensor is basically between the two rotating or items that provide the rotation, and therefore the sensor itself has to spin. Another way to measure torque, and we try to talk about this with customers as much as possible, is, you know, if you really want to measure torque, you might be able to do it using a load cell, and that's the least costly approach in many cases. These are two examples of eddy current dynamometers where a load cell is used to actually hold the housing of the dynamometer, and it's at a set distance from the center line of rotation, and so as the shaft inside spins, basically the housing wants to follow along, and you keep it from doing that with a load cell, and you can measure torque that way, and that works quite well. Again, certain installations lend themselves to this more than others. These eddy current dynamometers were designed specifically to be mounted that way. If you have a big electric motor that's mounted on a plate, it's a little harder to gimbal it like this. Also, if you have a situation where you want to measure torque, imagine like a big pipe you're trying to screw into another pipe, you want to measure the torque. It may be difficult to imagine a way you could do that with a torque sensor, but you can actually do it by using one or multiple load cells and applying a force at a distance from the center line. When you're talking about torque sensors, there are two basic types that come up frequently, and that would be either shaft or flange style. A shaft type sensor has a shaft, and the shaft can either rotate or not. There are certainly shaft style reaction sensors, and most of them are rotary though. And the shaft is either going to be smooth or keyed. And then there's also flange styles. And the flange is shorter, and it may bolt in easier, maybe not. If you have, say, a motor and a gearbox and they both have shafts, then shaft style sensor may be the best choice. Keyed versus smooth shafts. A smooth shaft works quite well with the appropriate kind of coupling. And the benefit of a smooth shaft is it applies the torque to the shaft in a uniform manner about the entire perimeter of the shaft. Or at a keyed shaft, you're actually applying a force at the keyway, and that translates into a torque, but that isn't necessarily a true torque. To avoid that, and also there's some backlash sometimes in keyed installations, so to avoid that, what we end up doing is doing a press fit on the hub and a keyed shaft, and that's not particularly good for torque sensors because once everything's together, it can be rather difficult to get them apart without damaging the shaft or the sensor. I've seen a lot of sensors that come in that are keyed, and the shafts are pretty well ruined from people pressing or removing hubs from them. A flange, you bolt it together, unbolt it, works quite well. These are some examples of shaft style sensors. On the right is actually a reaction sensor with a shaft. The other two are rotary sensors, floating or pedestal mount. Shaft saws are convenient mounting and can use a lot of standard style couplings. There's lots of different kind of couplings that work with shaft type installations. They're longer than the flange style, and so that can be a consideration depending on if you have a lot of space for your test bench or not. Rotating shaft saw sensors typically have bearings, and bearings can wear out, so that's a consideration. And they also, as we said, are available in smoother keyed shafts. These are some examples of flange style sensors, and they have a short length. They have better resistance to overhung moments. Imagine if you have a weight of a motor or something hanging on the sensor. The shorter the sensor is, the less bending you have in the sensor. They can be hollow. Sometimes people like to have hollow sensors to either run hydraulics or thermocouple wires or some kind of electrical lines through the center of the sensor. Hollow sensor can accommodate that. Bearingless rotary torque sensors also always tend to be flange style with few exceptions. Here's some examples of specialty torque sensors. Again, you say, okay, shaft and flange style are very common, but in some cases they're not necessarily the best approach. For example, if you want to measure pulley torque, it can be difficult to do that with a regular type sensor without having to install a bunch of different bearing blocks and things to support the radial load from the belt. And so a pulley torque sensor accommodates that. You can see up here on the left is a pulley torque sensor. The sensor would mount onto a motor shaft or a shaft, and then a pulley mounts to the sensor, and you can actually measure the applied torque through the pulley into the shaft. To the right is an actual torque coupling, and so this is special because it's a coupling that has been made into a torque sensor, and because of that, it's about as short as you can possibly get with an installation using shaft-to-shaft configuration. The shaft ends can come together almost as if this were an actual coupling, just a slightly little bit longer than the standard coupling. So about maybe an eighth of an inch between shaft ends, you could fit this sensor in. This one down the middle is a little micro capacity sensor, less than an ounce inch, and it has a flange on one side and then a little spigot on the other, and that spigot is used for the actual torque connection. Talking about couplings a bit. A lot of people don't want to use couplings because they can be rather expensive. It's not that easy to make them yourself, so you typically have to buy a coupling, and you know, it may be easy to conceptualize how you can bolt things together without using couplings. But in the end, all torque installations should use couplings. Some don't, but they all could benefit from it, and rotary ones particularly almost always need to have couplings. They isolate the torque sensor from extraneous loading, bending, vibration loads, those kind of things can be isolated using couplings. And also they prevent errors and damage. You can definitely ruin bearings and bend torque sensor shafts and wear them out if you don't use appropriate couplings. Basically, couplings come in single flex and double flex types. And single flex, sometimes called a half coupling, double flex, sometimes called a full coupling. Basically, the single flex has a single flex point, and that allows only angular deflection. Double flex coupling has two flex points. Essentially, it's two single flex couplings in one, and because of the two flex points, you can see it also allows radial misalignment, and there will always be misalignment between two shafts when you're doing installation. So if you have a motor and a gearbox and those shafts, you think they're true and parallel and in line, but reality is they're going to be offset a little bit, and the couplings allow that. And if not, if you bolt everything rigidly together, it induces bending and very serious loading into the bearings as the system spins. These are some examples of couplings. This is a disc type, and these are the kind that we recommend for torque measurement. They're very rigid, torsionally, and very soft in the angular deflection direction. You can see on the left there's a single flex, and in the center here is the actual flex pack or disc pack, and that's the flex, and the rest of it is quite stiff. A double flex basically takes two single flex discs and puts them side by side, and you end up with a double flex coupling. In the bottom middle, this is a spiral cut. These are popular. They rather hard to come by in the single flex variety, although that's the one that's shown here. More commonly, this would be considered a double flex, and you'd have a number of more cuts in it, so maybe 5 or 6 or 7 cuts instead of as shown here. Whoops. No. Some more examples of couplings. Coupling hubs are designed to mount on the shafts typically. They can either be keyed. This is an example of a keyed hub. This is an example of a kind of coupling that's designed to mount onto a smooth shaft. Again, we talked about keys. To avoid backlash, you really need an interference fit between the hub and the shaft. That can be very difficult, though. You probably have to heat up the hub, possibly cool down the shaft to get them together, but then to get them back apart without special equipment, that can be quite difficult. The shrink disc type, on contrarily, is designed specifically to grip onto the shaft and then to also be loosened and removed easily. And so if installed properly, these shrink disc types are also easy to remove afterwards. Bellows types, you can see we've got a couple different kinds of clamping hubs, and these basically tighten with the set screw and grip onto the shaft. This is a clamping flange style, so one side you've got clamp, one side you have flange. Bellows coupling is kind of a softer coupling than the disc type torsionally in some cases. They also are less strong, and that can be an advantage. Depending if you in your failure mode, it may be desirable for the coupling to tear into 2 pieces and act sort of as a safety valve, and the bellows couplings will tend to fail in that mode, whereas the disc type couplings, when they fail, they tend to take out more components as they fail. This is an example of a coupling using rope. We do not recommend this installation, but I thought it was kind of funny. You imagine this would need to be worked on and have the rope replaced pretty frequently. Don't do that. This is an example of a smooth shaft where the customer used a set screw, so basically a hub with a set screw to grip onto the shaft, and that's typically not going to work for anything but the very smallest torque levels. And so as you can see here, the set screw actually spun, or the hub spun and scored the shaft. So this basically ruined the shaft. Don't do that. See, this is another picture of the same sensor. I guess after it spun, customer attempted to fix it by machining some flats, or maybe they machined the flats first, I'm not totally sure, but it spun anyway. And it actually spun so much and got so hot that it melted the housing. You can see up here, the lid actually got so hot, the aluminum melted so much that the cable actually was able to kind of fall down into the housing. So this is kind of an interesting application. This isn't normal or typical, but it's what can happen. You can generate a lot of heat when you have slipping parts. Don't do that. Floating versus fixed mounts. A floating mount installation is where the sensor is supported only by the drive and load side connections. And so it basically floats in the middle between 2 components. And a rotary sensor, the housing is going to want to rotate along with the sensing element, and so a flexible strap is used to keep it from rotating. Bearingless sensors are always floating mounted because they don't have any bearings, so it cannot be supported except by its end connections. Now, a fixed mount installation really only applies to sensors that have bearings, and that is when you actually take the housing of the sensor and mount it to a fixed support, and that takes a different type of coupling than a floating mount. A fixed mount, you have alignment between the sensor shafts, each sensor shaft, and the item that it's being attached to. This is an example of a floating mount installation. You have a single flex coupling, which is shown here in this little diagram. The torque sensor floats in the middle. You imagine your drive shaft and the shaft on the loading item aren't perfectly in alignment. You end up with basically a big double flex coupling in the middle. So you've got 2 flex points separated by the sensor. And so this kind of arrangement allows relatively more misalignment between the drive and the load than a fixed mount. It's relatively easy to install. There's a picture here that shows a actual installation using single flex and floating mount. Pros, like I said, relatively more misalignment. The sensor is protected from radial and thrust load damage. Imagine you can't really ruin the bearings by applying radial loads if you float the sensor in the middle of two flex couplings. Relatively lower cost. The sensors tend to be at least a little bit less expensive when you go floating mount style, and the couplings are less expensive because a single flex is typically going to be less expensive than a double flex style. Cons are the sensor is unsupported during a change of a test article. Imagine if you have a motor and a torque sensor and you want to test a bunch of different pumps. Every time you disconnect a pump, the whole drive line is going to sag. You have to support it. A pedestal style sensor would prevent that. Also, you have more unsupported rotating mass in a floating style than if you had a fixed mount. And then also, in a floating mount, it's important that the sensor actually floats. A lot of people have a tendency to want to bolt the housing to something to keep it from spinning, and that may be much more tightly connected than it should be. It should truly float with a rubber spring or some kind of a flexible mount. As soon as you try to bolt the housing to something, it pulls the housing towards that item and starts to put a radial load into the bearings, which is undesirable. This is an application example of a fixed mount where you see you've got double flex couplings. The torque sensor is mounted. This is a little picture basically of a fixed mount sensor where you've got a double flex coupling on the bottom, and then this is actually a rigid coupling, but there's a slip joint here where another item fits in, so it essentially becomes a double flex on this end as well. Pros of fixed mount: the sensor's supported while you're connecting and disconnecting test articles. It can be better for high speed because it has a shorter rotating length. The cons would be that it requires a little more expensive couplings, relatively less misalignment capability, and the sensor can be damaged by unsupported masses, radial and thrust loads, and that's important. We want to avoid damage to the sensor if at all possible. In case there may be radial loads, another bearing should be used. The sensor is never to be designed into the system to be used as a bearing block. It will be destroyed. Other possible installations: this is acceptable but not necessarily desirable. You have a rigid mount, a floating sensor, and then a double flex on the other side. Bearings versus bearingless. Some people ask, well, why would you want a bearingless sensor? Sometimes bearing friction becomes important. Imagine if you're actually trying to test bearing friction. You might not want to have the bearing friction of the sensor be part of that test, so a bearingless sensor may work. Bearings do provide alignment between the sensor and the rotating and the stationary parts of the sensor. In a bearingless sensor, the user is required to maintain that alignment, and so it makes installation a little more tricky. Bearingless are always floating mount. And once again, I'm going to say a pedestal or foot mount sensor must never be considered as a bearing block. It's just to allow the sensor to be positioned, but it's not supposed to allow radial loads and things into that sensor bearing because it's not designed for that. Accuracy resolution, usually quoted as percentage of capacity, and that's usually the easiest spec to pull out. For example, a 0.1% combined error sensor, you calculate that would be plus or minus 0.1 Newton meters of error, so that could help you decide if that's an appropriate sensor to use or not by looking at that factor. But that doesn't take it all into effect. If you look at a sensor data sheet, there's a lot of other specs besides the accuracy or combined error spec. Temperature, noise, measurement bandwidth, those all come into play. Temperature error can be important or inconsequential. If you have a test where you're going to be seeing large temperature shifts during the testing, temperature compensation of the sensor and the temperature specification is very important. Noise and resolution. If you have a lot of noise, you can have some trouble making the measurement even if the sensor is quite accurate. And so that has to do with the instrumentation possibly attached to the sensor, environmental noise. So noise can be a limiting factor, and that can be a little hard to pin down. Resolution talks about what is the smallest discernible change in torque that you can actually measure. Again, if the noise is greater than the actual measurement resolution, you may not be able to make full use of that. You may have to filter. Again, if you're filtering, you're reducing the bandwidth, and with reduced bandwidth, you may get some pretty significant errors. If you're trying to, say, measure something that's happening at 1,000 hertz and you're running a 200 hertz filter, you're going to be basically attenuating that signal, so you may have a very large significant error due to the filtering. When you're choosing a torque sensor, there's always a compromise between the accuracy and the resolution and the safety factor. So people tend to want to adjust the sensor size down to meet the capacity of their measurement or their expected measurement range. But the reality is you have to be careful because you don't want to overload the sensor. And so making the capacity of the sensor and the measurement range too close to each other can invite damage to the sensor. Quick look at these specs. Basically, you see there's a bunch of different specs listed: combined error, non-repeatability, temperature effects, and resolution and sample rate. So those all must be considered when you talk about what kind of accuracy you're going to actually get out of the system. Different signal types: 5 volts, 10 volts. A lot of the sensors available with either 5 or 10 volts. People ask, well, which one is better? Well, it really matters just to match the output of the sensor to the input range of your data acquisition system. So if you have a 10-volt input range or a 10-volt input range, you should select a 10-volt output from the sensor. But it's not necessarily better or worse. It just matches. And then frequency: if you have the ability to measure frequency on your data acquisition, the frequency output can be desirable. USB and 485 are examples of digital output. We can also do Ethernet. Those sort of outputs are digital, which can eliminate some errors. Imagine if the sensor itself is digitizing right at the rotor, and then the data remains digital all the way through. You prevent or eliminate a couple different conversions, one from digital to analog and then one from analog back to digital in the data acquisition. So we'll keep going. When talking about capacity selection, torque sensor must accommodate the maximum expected torque for the application. The overload range is reserved only for the occasional accident, so you'd never plan on using anything more than the capacity of the sensor. In many cases, torque is a little harder to sort of get a feel for than load. How much torque is there really in the system? A lot of times people have to calculate it, and so you can do that by looking at the horsepower and the RPM. And once you have that, it's called the average running torque. And then there are load and drive factors that can be applied to that to actually estimate what the probable peak torque may be. And it can be considerably higher than the average running torque. You also need to consider startup and inertial loads and any extraneous loading. Drive factors: you imagine if you're trying to spin your system using something like a smooth turbine, that's quite easy and smooth. On the other end of the spectrum, down the bottom list, would be, say, a 4-cylinder gas engine, where each firing of the cylinder creates a torque spike. That'll be a relatively difficult drive factor. Same thing with load. If you're spinning, say, a fan, it's quite easy to spin. Imagine on the other end of the spectrum, if you're, say, having full torque reversals, or you're, turning some kind of a grinding system where it's like a hammer mill or something, you may have a relatively difficult load. And so you basically take the average running torque that you calculated and you multiply by load factors to come up with probable peak torque. And then you need to size the sensor using that peak torque. Then you also think about starting conditions. If there's a high inertial load and you start a motor, sometimes you can exceed the rating of the motor dramatically. There's a startup torque that's much higher than the running torque of the motor. And the way to prevent that would be to start softly. Also, if you were to hit an emergency stop, and same thing, if you shut everything down very quickly, the rotary inertia can overload the system before it shuts down. Just remember, peak torque can be as much as 10 or more times average running torque, so very important to consider it. That brings us to dual range sensors. Well, dual range sounds awesome. If you have a high peak loads, but you want to measure very small torques, how about a dual range sensor? And in fact, many customers do use them with great success, but they're not a magic bullet. They're very convenient. They can allow much fewer fixture changes, and they can allow a lot more safety factor. But with a dual range sensor, you have to worry about noise. The small range, you're typically going to have more noise on the small range, so you may have to do more filtering. There's some temperature sensitivity of 0, which can be more of a factor on the low range measurement. And also you end up using larger fixtures. Imagine if you're trying to test 2 different pump sizes, but you're using a dual range sensor. you're always going to be using the full size sensor even to measure the small pump torque. And so the couplings and the fixturing you use to adapt to the small shaft are going to be dictated by the large form factor of the upper size of the range sensor. RPM considerations. Every sensor will have a rated RPM, but it's important to remember that just because a sensor is rated for a certain RPM, it doesn't necessarily mean it can just be run at that speed without worrying about balancing and everything else in the system. The sensor is only one part of the rotating assembly. In some cases, for high-speed operation, the entire string must be balanced in place. And the limit on the sensor as to how fast it can spin may be bearings, it could be balancing, sometimes it's actually G-forces on the rotating parts. It's going to depend on the actual sensor to decide what's the limiting factor. Common features that people like to see in a torque sensor, sometimes hollow is good. Again, you can run electrical or hydraulics through the center, and that could be handy. Scalability means you can change the output. Certain sensors you can select either 5 or 10 volts or various frequencies. You can also change the scaling. So one day you could have 10 volts equals 100 Newton meters. The next day you might have 10 volts equals 200 Newton meters. And that can be useful if the sensor is used for multiple tests in a facility where you don't necessarily know what it's going to be used for from one day to the other. Filter levels, again, data acquisition, you can do filtering, but in some cases people want the signal to be less noisy coming straight out of the sensor. Therefore, you want some filtering in the sensor. If those filters are adjustable, that can be handy. If they're fixed, it's important to understand what they are and what the limitations may be. There are also some sensors that allow quite high RPM. One example of that is our Model T25, which has a special bearing design, which basically shunts all the bearing friction over to the drive side and removes the bearing friction from the measurement, and also allows for higher rotary speeds. Got some torque examples of applications. This is an interesting test, actually. It's a brake test, and we have a Model 5400 series reaction torque sensor. So the torque sensor isn't spinning, but it's attached to this shaft that then holds onto a brake caliper, and then there's actually brake disc that spins. And you can see in the picture on the bottom left, some of these tests, the brake disc can get quite hot, and that's the actual reason for this sensor to be removed physically from the brake disc. So it's kind of far away to limit the amount of temperature that makes its way down to the torque sensor. But this is using a fixed torque sensor to measure a rotary torque. Fuel pump optimization. We had a customer who wanted to measure optimization, or wanted to optimize a fuel pump. They were a race team basically, and they're trying to tweak various parameters. And so they built a little flow bench where they have a motor that spins the fuel pump, and then they can measure the flow and also how much power it takes to create that flow at various different RPM levels. You can see this is a fixed mount design with double flex couplings on each side. Another example is an engine supercharger power consumption, where a customer wanted to measure how much power does it actually take to spin this supercharger as they make various changes to the design. And so this uses a pulley sensor that's mounted on the engine shaft, and then the belt actually is driven by that pulley and drives the supercharger, and they can actually measure in situ as they tune the engine and play around with the supercharger. Steering column tests, another interesting test where we use a reaction sensor to make a rotary measurement. You can see in this picture there's an encoder, and that's separate from the sensor, so the customer can actually measure the degrees of rotation. And then we have a motor that drives through an MRT into the steering column, and basically they're flexing or twisting the steering column back and forth through about 45 degrees, and they're just basically studying the wear characteristics of the steering column, simulating actual use as you were driving down a highway, for example. Last but not least, we have done some work with one of the colleges that does a Formula SAE car, and they're entering an electric vehicle which is pretty interesting. I guess they're allowed to enter electric vehicle or a gas, so they've went electric. To do that, they had to redesign the entire drivetrain of their vehicle, and they're using 2 electric motors, one at each rear wheel. And those motors need to be characterized, and they need to develop control algorithms and performance characteristics of those motors. So what they did is they made a test setup where they have 2 electric motors, so one at each wheel, and they're actually testing the motors against each other. And so this isn't in the car, obviously. They just mounted the motors, and they put one of our HRDT rotary torque sensors with integrated couplings in the middle. And so they're basically testing one motor and using the other motor as a load and vice versa. And here they can test regenerative braking and performance characteristics. And that's it. By the way, this isn't actually the SAE car. This is our famous Brian Peters from Interface, who's I think the 5-time national champion autocross in I think 5 different categories. So congratulations to Brian. Anyway, that's it. Does anybody have any questions?